Okay, if we could just focus on this for a moment, just in case you may have some doubts about what's going on here. Let me have your attention. X is in the polyhedral set, so C transpose X, which is by definition C transpose is the summation AI here, will be greater than or equal to BI, sum of the BI's, because each AIX is greater than or equal to BI, term by term. Okay? That's why you've got this, which we know is equal to that. Now, for the equality to be possible here, so just a side note, equality is possible if and only if, of course, each AIX term by term equal to BI for I in the active set or in the index of the summations. Okay? And for that reason, you end up with this system. And this system, Jx bar, contains n linearly independent AI in it. For that reason, it admits a unique solution, which is what we argue here. And if it admits a unique solution, equality is possible if and only if x and x bar are the same. For the remaining case, when x is different from x bar, you've got only strict inequality being possible. And that, of course, proves this. So x bar is a vertex of the polyhedral set under consideration. Okay? Any questions on any of the previous stuff? You might want to work out these proofs on your own. I mean, not just going through the proofs, but when you have a clear mind in the morning, sit down and try to work out a proof, because if you're not working out the proof actively, you don't really understand this stuff. Okay? Understanding someone else's proof is not enough, believe me. I know that for sure. Working it out on your own makes you really absorb the material better. Okay? So, make a habit of that. So let's continue with some additional concepts here. Well, before I go into new stuff, maybe we should add a remark here. What did we show for the basic solutions? The property of being a basic solution depends on the representation. That's example demonstrated that. How about here? The property of being a basic feasible solution. Well, you have a basic feasible solution if and only if the same point is also an extreme point. So it does not really depend on the representation. Okay, that's important. Because basic feasible solutions are the same as extreme points, and extreme points don't depend on the representation. You have a set, and it doesn't matter how you represent that set. Let's talk about adjacent basic solutions now. We say two basic solutions are adjacent if there are n minus 1 linearly independent constraints that are active at both of them. So, the active set corresponding to the 2 points, when you intersect them, you will be able to find n minus 1 or more linearly independent constraints in them. Okay? Here's an example. I keep using the same example, but it works fine. Okay? So P is here. Let me call these points x1, x2, x3, x4. These are the extreme points of P. And let's call x5 and x6 here. Basic solution, points that are outside of polyhedral set. So in this case, x5 and x6 are basic, but they are not feasible solutions. The remaining ones are basic feasible. Now, if you look at x5, for example, x5 is this point. It's got x4 as an adjacent basic solution. Also, x1 is an adjacent basic solution, even though the picture does not really tell you that. Okay. All right. So x5, x4, x1 are adjacent basic solutions. We're not talking about feasibility here. We're talking about basic, adjacent basic solutions, because they share n minus 1 linearly independent constraints. N equals 2 here. And so there's only one constraint that are shared by each of these points in their active sets. Okay? Each contains this particular constraint. What was the name of this? 1, whatever. Let's call it 1, 2, 3, and 4. So each of them contains 1. Okay. What about x6, x3, and x4 and x3? They are also adjacent because, again, their active sets each contains number 4. Okay? Let me also define edges here, or edge. If x bar and x cap are adjacent basic solutions, and if they are also feasible, so if they are adjacent basic feasible solutions, so don't, in that one we did not really talk about feasibility. Okay? Over here we have feasibility as well. If there are adjacent basic feasible solutions, then the set of points that the line segment connecting them is called an edge of P. Okay. The line segment between x bar and x cap is the set of all points that can be generated as a convex combination of these 2 points, right? That's the definition of line segment. Now let's continue with polyhedral sets in standard form. In case I did not mention it before, polyhedra is the plural of polyhedron. Polyhedron is the same as a polyhedron is a polyhedral set. Okay, so let's define P to be the set of points x for which ax equals b and x greater than or equal to 0. That's the standard form polyhedron. Equalities and non-negativity on the variables, okay? That's how we define standard form. So in this case, when you talk about a basic solution or a basic feasible solution, you are, at least some of you, are quite familiar with basic solutions and basic feasible solutions in this particular context. Up to now, we were in a more general context where the polyhedral set was defined in some arbitrary way. Okay? Arbitrary meaning with inequalities of any kind and not necessarily non-negative variables. Okay? All right, so in this case, what is the definition of a basic solution and a basic feasible solution? Who would like to volunteer for an answer? You know this. Some of you do. How many people know this? Raise your hand. I want to see at least. Only one person? Come on. The other guys and girls. You know it, but you don't know you know it. Huh? Maybe. You know it? You seem to be... You're not sure. You're not sure. Okay. Sibel, what is the definition in this case? Or what is the counterpart?
Basic solution is a basic feasible solution if it satisfies the other constraints.
Right. But, well, we also have the same condition with the general definition. So that doesn't really tell me. In this case, what is the situation? You have a special case here, right? You've got ax equals b, x greater than or equals 0. This is the system we're talking about. Let's assume without loss of generality that the rank of A is m. And of course, we're assuming A is m by n. Okay? It's got m rows, n columns, and the rank is m. It's the row rank. Now, why is this without loss of generality? Because if the row rank is less than m, all you have to do is you use certain equations to eliminate certain variables. You eliminate as many as necessary until you get a system which looks like the following. A prime x equals b prime. Okay? A bunch of rows are eliminated. we can get this with rank A prime being equal to the, say, K, where A prime is now K by N. Okay? So you can always reduce your system to this particular form where the number of rows is the same as the rank of the matrix. All right. You can do that by elementary row operations. You know, it's always doable. All right. So under this assumption, with this assumption, so this is just a parenthetical remark, we can get, by elimination, this kind of a system. In this case, I've got M here, M constraints, equalities. And then I've got how many? N inequalities. So the total is M plus N. You've got M plus N inequalities as a total. How many do we need? We need N linearly independent active constraints for a basic or basic feasible solution. Okay? Now, those n linearly inequalities, n linearly independent active constraints, they should surely include AX equals B, because that's part of the definition. So, M of them come from AX equals B. Okay? They must be in your active set. The remaining ones, N minus M, come from the non-negativity part. Okay? You've got, of course, too many here. You've got N inequalities of the second kind or of the non-negativity kind, and you need only N minus M of them. So the ones that you choose as active will become 0 because, you know, this simply says that xj is greater than or equal to 0 for every j in the set, say, I, going from 1 to n. So let's just define I to be that set. Okay? And if you take xj greater than or equal to 0 as an active constraint, xj becomes 0. That's it. All right? So we pick n minus m of the inequalities xj greater than or equal to 0 for j in I as active, which means that we take them as xj being equal to 0. Okay? For those n minus m of them. The solution so obtained, the solution to what? The solution to the original system. So let's give a name to this. What is the name of this? Let's just call it 1, for example. Okay? The solution to the system 1 consisting of AX equals B and X greater than or equal to 0, so obtained meaning that xj are set equal to 0 for n minus m of the variables, is a basic solution if what condition is satisfied? Linear independence of what? Yes, you're right, but of what? No. Columns. Columns. If the m columns of A that are associated with the m variables that are not picked. The ones that are picked are those that you set equal to 0. And so the remaining ones are m. N minus m of them are set equal to 0. So with the columns of A that are associated with the m variables that are not picked and that are being solved for, are linearly independent. Well, this is not really confusing, but let me just explain this maybe in the following way. So let's define I sub n to be the set of indices of the variables whose non-negativity constraint is taken as active. Okay? Those are the ones that are set equal to 0. Let IB be the remaining set of indices. Okay? So IN has n minus m indices in it. IB has m indices of the indices of the remaining ones. Partition A into submatrices B and N, where B contains, or B is the matrix consisting of those columns. Remember, A sub j is a column vector. That's the jth column of A matrix, corresponding to those in I sub B. Okay, that's the submatrix of the columns in of the indices in IB, and N is the submatrix consisting of those columns whose associated variable is in I sub n. Each column is associated with a variable. So columns and variables, they always go hand in hand. Okay? So what is the size of B? You've got how many elements in I sub B? M. So you've got m rows, the rank is m, so this is m by m. It's a square matrix, okay? This part has, again, m rows, but the number of columns is n minus m. Okay? That's the way we partitioned. With column rearrangements as necessary, I can write A as consisting of these two submatrices with column rearrangements as necessary, because normally the first m columns need not be in B. Whatever columns are in B, just put them at the front, and so they constitute your B, and the remaining columns, n minus m columns, constitute your n. Okay? All right, so partition X in the form, say, xb, xn, where xb is the column vector consisting of those variables whose indices are in I sub b, okay? And x sub n is the column vector whose components are those that are in I sub n. So this is a column vector. It's got how many? It's m by 1, okay? And this one is n minus m by 1. Then we can rewrite the system ax equals b and x greater than or equal to 0 in the form, in the partition form, as the following. You simply take the partition B and xb, xn. So x is a column vector. Now in this, arranged in this way, A is your matrix, equals B. When you multiply them out, also let's write xb and xn greater than or equal to 0 as a vector. Okay. When you multiply them out, you get bxb plus nxn equals b, xb greater than or equal to 0, xn is equal to, well, greater than or equal to 0. That's the way we have. So, over here, I'm taking the variables whose indices are in the I sub n set as active. This part is also by definition active. And we have n constraints that are active. Whether or not they are linearly independent, we don't know, but we've got this. So, with these things being active, of course, this gives the following system. xn is equal to 0. Now, okay. xb, I don't know. I just ignore it. The first part, bxb plus nxn is equal to b. So, this portion here we ignore. Why do I ignore? Because I'm interested in finding n linearly independent active constraints to obtain a basic solution. If the solution obtained happens to satisfy the ignored constraints, fine, it's a basic feasible solution. If it doesn't satisfy, it's just basic but not feasible. Okay? So, and of course this system becomes even simpler since xn is equal to 0. This reduces to bxb equals b. Okay? So, what you want is, in order for this solution to be a basic solution, you want these to be linearly independent. And of course, that means the columns of B must be linearly independent. Otherwise, it doesn't work. Okay? If the columns in B happen to be linearly dependent, you either have no solution here, or the other possibility is you have multiple solutions. But in both cases, you don't have a unique solution. You want a unique solution here in order for this to be basic. Okay? So, So to get a unique solution to this system, which is nothing but Bxp equals B, we require the columns in B to be linearly independent. So that Bxp gives you a unique solution, which allows you to construct a unique solution to the original system. If this is the case, then of course the solution for Bxp is the inverse of B times B, solves Bxp equals B uniquely, and the solution with xp part consisting of B inverse B and xm part consisting of a vector of zeros solves the system Bxp plus nxn equals B and xn equals 0 uniquely. Okay? Because that system is nothing but this Bxp equals B system. They are the same. Okay? All right, so you recall these things from at least some of your earlier education, and this should make more sense to you. Let's state this as a theorem. I'm not going to prove the theorem because the main ideas are already transparent. Let's just state it. What number am I at? 4? Okay. Theorem 4. For a standard form polyhedron P defined by AX equals B and X greater than or equal to 0, where A is m by n with rank m without loss of generality, a point x bar in the n-dimensional space is a basic solution if and only if Ax bar equals B and there is an M element subset I sub B of I consisting of all column indices such that two conditions are fulfilled, A and B, such that the columns AJ for J in I sub B, these are the columns that go into B matrix, are linearly independent. And part B, the components of X bar are equal to 0 for those J in I sub n which is by definition the complement of I sub p in the index set of the variables. Okay? This summarizes all we have done. Of course, you need to prove this is an if and only if statement, so you need to prove this both ways, okay? Both necessity and sufficiency. I argued only for one of them. The other part, it's your job to do it. Nice exercise for you. I hope. Sometimes, of course, you expect students to prove something in maybe in a matter of a few hours. And then after 3 weeks, somebody comes along, he says or she says, I've been working on this proof for 3 weeks and still I haven't been able to do it. Or I did something, but whether or not right, I'm not sure. Then I check it, it's wrong. It's all wrong because, you know, the viewpoint is not really proper. First, you must have the right viewpoint. So work on these things. I mean, you know, practice makes better. Not perfect, perhaps, but better. Maybe I should give you an example and then we finish up. All right, so given this A matrix and B vector, the standard form polyhedron is defined by these pair of equalities and the non-negativity, okay? So in this case, let me take, for example, B equals something and N equals something else. For x and, let's see, I happen to pick x3 and x4, so the columns associated with x3 and x4 are -5 and +5 and -4 and -1. That's how you partition. These are the variables that we are going to set equal to 0, okay? And these are the variables, x1, x2 are the variables that we will solve for. In this case, we've got 4, 1, 3, -1. So I'm going to take these and take them as active. That's why your x3, x4 happen to be in I sub n, or, you know, this is the way you've got the matrix. And of course, these are also active, always. So the system we have with these active ones reduces to 4x1 plus 3x2 minus 5x3 minus 4x4 equals 1, x1 minus x2 plus 5x3 minus x4 equals 2, x3 equals 0, x4 equals 0. That's the system you've got. You're in 4 dimensions, and you've got 4 equations that you hope are also linearly independent. Okay? Now, of course, with x3, x4 being equal to 0, obviously you've got 4x1 plus 3x2 equals 1, and x1 minus x2 equals 2. That's what it gives you. And you can see that the columns here, 4, 1, and 3, minus 1, are linearly independent. Columns in B, which consists of 4, 1, and 3, minus 1. So the resulting solution is basic. What is the resulting solution?
1 minus 1.
xb, x1, x2 equals 1 and minus 1. That's the resulting solution for this part. And for the actual vector, xb, xn, x1, x2, x3, x4, the solution is 1 minus 1, 0, 0. Is basic for the original system, for the 4-dimensional system. Okay? So there's an interplay between the 2-dimensional or the m-dimensional and the n-dimensional, which is quite obvious here. And is it basic feasible? Not feasible. But it is basic okay. You can try out other basic variables or basis matrices, B matrices, and see what you come up with. Okay? I'll let you go at this time now.